Hello, welcome to watch our tutorials for probability and statistics. In this video, we will talk about means and variance of nonlinear combinations of random variables. So in many scientific situations, we want to know the linear combinations of random variables and their statistical analysis. So for example, z equals x divided by y. This is a linear combination of x and y, and x, y, and y are both random variables. We only know the distribution and the statistics of x and y. But if we want to know the distribution of z, for example, we want to know the mean or variance of the z, but usually because they are nonlinear combination of two random variables, so usually the mean of z is not necessarily equal to the mean of x divided by mean of y. So this is only in very special circumstances they are equal, but usually they're not equal. So the general solution for EY or variance of y can be very difficult to find. Depends on complexity of the function g. So this is the function. We can say the gxy. But we can use some approximations available that depend on a linear approximation of the function gx or gxy. For example, suppose if we denote ex as mu and variance x is sigma x squared for the variance. So a Taylor series approximation of gx around x equals mu x can be given as gx. This is a nonlinear combination of random variable x, and we can use the Taylor series. So this is equal to the g function at mu x. Evaluate the g function at the value equals x equals mu x, then plus the g function, the derivative with respect to x, then also evaluate x mu at mu x, then times x minus mu x, then plus the second derivative of gx with respect to x, and evaluate at the value at mu x, then times x minus mu x squared divided by 2, and so on. So in this case, if we truncate after the linear terms, if we truncate all these terms, only left this one. So the approximation of egx, then we take expectation egx then equals g mu x, right? This is a linear, certainly the very simple approximation for the gx. So which means egx expectation of the gx is the g of the expectation of x, approximation. However, if we include the second order term of the Taylor series, so we have a second order adjustment for these first order approximations as egx also equals g mu x plus the second degree of derivative of gx over x, also evaluate at x equals mu x, then times sigma squared divided by 2. So if we look back, so if we cut here, take the mean, then this term will be 0, so only this one left, right? But if we keep all these three, then take the mean, then this one left, and the second one also left, because take the mean of this one comes to the variance of x, which comes to this approximation. Though this approximation is more exact than only with this term, right? we take a look at an example. Give the random variable x with mean, mu x, and variance sigma x squared. So give the second order approximation to the function equals ex power. Ex power. We take e means mean. We'll try to calculate the mean value of ex. So the solution is first, this is the gx, right? So ex is the gx. So we take ex derivative over x equals ex. And the second order derivative also equals ex. Then we fill in the two order approximation formula and take expectation. Then we can get ex equals e mu x times 1 plus sigma x squared divided by 2. And similarly, you can also develop an approximation of the variance of gx by taking the variance of both sides of the first order Taylor series expansion of gx. So the variance of gx equals partial, so gx take derivative, then take square, then evaluate at x equals mu x, then times x times the variance of x. So the example is we also want to calculate the variance of ex now. So because the first derivative equals ex, then we fill in this form the variance of, here variance of ex, have to variance of ex equals e 2 mu x in the power, 2 mu x in the power, then times sigma x squared. And these approximations can be extended to nonlinear functions of more than one variable. So given a set of independent random variables x1, x2, until xk with means mu1, mu2, mu_k, and the variance sigma 1 squared, sigma 2 squared, until sigma k squared. So if we let y equals a function called h, which is the function combination of x1, x2, until xk, is a nonlinear function. So the following are approximations for ey and variance y. So this is the approximation for the expectation of y. Evaluate the second order of Taylor series approximation. So ey equals the function h evaluated at mu1, mu2, mu_k, then plus a combination of k terms, each term equals each variable's variance divided by 2 times the second order derivative of h function over this variable, then evaluate at its mean. And the variance of y is the summation of k term. Each term is the first derivative, take square with respect to this variable, and evaluate the mean of this variable, then times the variance of this variable. So the example is consider two independent random variables x and z with means mu x and mu z, and variance sigma x squared and sigma z squared respectively. Then consider a random variable y equals x by z. So the question is give approximations for ey and variance y. So the solution is first we calculate the first derivative of y over x and y over z, and second derivative of y over x and y over z. Then we fill in this to the form for the approximation of ey. We'll get ey equals the mean of x divided by mean of z, then times 1 plus sigma z squared divided by mean z squared. And approximation for the variance of y, after we have fill in these derivatives and some mathematical manipulation, we can get variance of y equals 1 divided by the mu z square, then times the variance of x plus mu x square divided by mu z square, then times variance of z. Thanks for watching.